Okay, in this video, we're going to look at the idea of electrical circuits. And this is a really important aspect, and it's something that hopefully by now you already understand because of the first light bulb lab, right? So the idea in the first light bulb lab was to take a light bulb, a battery, and a wire, and to connect them in such a way that you would end up with the light bulb lighting up. Now, the only way that that is going to work is if you create an electrical circuit. You may not have known that at the beginning when you started doing this, but hopefully now you have a good understanding that in order for electricity to flow, you must create a circuit. And a circuit is just simply a closed loop. Now, one way that you would know if you really did have a closed loop is if you started at a point and you were able to follow the path in one direction and you eventually return to the starting point, then that is a circuit. So, for example, in racing, sometimes they have things called road races where they just race from one place to another. And then other races are called circuits. The circuit specifically refers to not a circle, but just simply some kind of track in which you can start in one point and then you end up back in the same place. So, for example, a river would not be an example of a circuit because the river starts at one end with its springs, and then it eventually continues to go until it empties into a lake or into the ocean or into the seas. And so that's a one-way path. You don't return back through the river. You don't return back to the original place. So we can draw a closed loop any number of ways. Remember, loops do not have to be a circle. It can be any shape that we want it to be. But what must be important is that it must return back to the original place. Now, when you were trying to light the light bulb, I'm sure you found all kinds of situations where you just connected the wire over to the bulb over here, and then you connected the battery over here, and nothing happened. Because it was important to bring them together to close off the loop. You should think of electricity as very much like water. If you do not have a system that closes back on itself, then the water cannot flow. So the water is going to be stopped from being able to flow. So this is a circuit, while this guy is not a circuit. And it's not a circuit because it does not return back to the original point. Right? And this is probably what a lot of the failed methods of trying to get that light bulb light probably looked a lot like this. One object on one end, one object on the other end, battery and light bulb on either ends, and just nothing is lighting up. Even touching the battery to the bulb doesn't make the bulb light up. You must create that loop so that the current can flow, because the current cannot be collecting somewhere. So let's say, for example, that I had 5 amps passing through this spot on the circuit. Well, if I were to look at this point, and let's say, for example, I only saw 2 amps, where are the other 3 amps? Where did they go? That would be a violation of conservation of charge, that the current must be the same everywhere in this circuit, because otherwise charge is somehow disappearing from the system. So if 5 amps passes through this point, that means 5 coulombs of charge passes by every second. Therefore, every other part of the circuit must also have 5 coulombs passing every second. Otherwise, charge is disappearing, or maybe charge is even coming in. If I see 5 amps here and I look somewhere else and I see 6 amps, where is that other amp coming from? There's no source for that other amp to come from. So this idea of closing off the loop allows the current to flow. And once you close off that loop and you supply it with a power supply, the battery, then the charges will begin to move, and you'll see something happening. Either the light bulb will light up, or at the very least you'll be able to measure that there is some actual current flowing through there. Now, there is a little bit of a kind of a complication, and this is a little bit unfortunate. It's just sort of a historical thing that when Ben Franklin was doing his early work, he decided to use the convention that everything would be based on the movement of the positive charges. He based everything he did. He just assumed the positive was the more important one and the negative one was the other. But in reality, it turns out that actually everything is about the negatives, those electrons. The electrons are the ones who are actually doing the movement. But by the time people realized that that was what was happening, that it was really about the negative charges moving, the convention had already been established that everything was based on the flow of the positives. Everything was based on how the positives move, even though in reality they don't actually move. So this brings us to something called conventional current, as opposed to the other, the opposite of the conventional current would be the electron flow. So let's say, for example, that we apply an electric voltage to a wire what we will actually find, if we could shrink ourselves down and we could get inside of this wire, is that we would find that the negatives are moving in this direction, for example. So the electric potential is there, there's an electric field in the wire, the electrons are beginning to move, they're beginning to flow, just like water flows. They begin to move in a cohesive direction. That's what a current refers to. It refers to a group of objects all moving in one particular direction. You'll see that word used lots of ways. Obviously, we use it for water, we use it for electricity, but you can even use it for other things like ideas. This idea that there is some current, some idea that is somehow moving forward, moving in a particular direction. So the idea that the electrons are flowing in this direction is opposed to what we use and what we refer to as the conventional current. And the conventional current is the movement of the positive charges, even though in reality, again, the positives really don't do very much moving very often. So this is electron flow on the bottom. That's what's actually happening. And then on the top, we have something called conventional current. And that is what we are going to use for the remainder of this topic. We will always be using the conventional current. It will be assumed that if you use the word current, you mean conventional current, and that if you want to talk about the movement of the negative charges, the electrons, then you will use the word electron flow, and you will not use the word current at all. So the word current always refers to the direction of the positives. Now, let's look at what's really happening. You really have these little atoms strung all throughout the wire there, with their positive charges deeply embedded down at the center of the atom, and then out at the outer edges, you have these electrons that are able to move. So if you imagine the positive charges are all fixed in place, and the negatives move in this direction. Okay, but there's no difference between me taking the electrons and let me hold them in place. I'm going to grab all the electrons in the wire, all those free electrons, I'm going to hold them in place, and I'm going to start pushing the atoms. Now when I push the atoms away from that, those electrons, those free electrons, I will get positive charge starting to move to the left, while the negative charges will stay essentially locked in place. Is there a difference between these two things? Or are they basically the same thing? Well, they are basically the same thing, because look, the important thing is the relative motion. So I have the positives moving to the left relative to the negatives. I have the negatives moving to the right relative to the positives. Now, does it matter whether it's really the negatives doing all the movement to create this relative motion, or all the positives are moving to create this relative motion, or maybe they're both moving? It really doesn't make any difference at all. It's exactly the same thing. The amount of energy that's going to be carried, the amount of charge that is moving, everything is exactly the same. It's just really an issue of notation. How do we note the direction that the charges are moving? And again, it's just a historical artifact. I mean, in reality, the conventional current in some respects is wrong, because it doesn't really represent what is actually physically happening. But it turns out that it doesn't matter whether I make the positives move this way or the negatives move this way, or they're both moving. The relative motion is that in this particular drawing that I've drawn right now, the negatives are moving to the right relative to the positives, and the positives are moving to the left relative to the negatives. It doesn't make a difference who is actually doing the moving, because the results of all the energy and the amount of current and any other property that we could really measure is still going to function exactly the same. The only difference would be is if you could go down and see at the microscopic level what was going on, you would see that it really wasn't the positives doing the moving. It was really because of all of these negative charges doing the movement. Okay, so conventional current, that is something you're being asked to know, that the direction of the conventional current is the direction that the positives flow, as opposed to the other thing, which will be the electron flow. Okay, now ultimately we're going to start to draw some new kinds of diagrams. You know, we've drawn free body diagrams, we've drawn vector diagrams to represent the vector properties. And now we're going to draw a new kind of diagram. It's called an electrical diagram, or a circuit diagram. And in order to do that, we really want to have symbols, because we don't want to have to draw, you know, just like we did the free body diagrams, we don't want to have to draw elaborate pictures of objects. You know, this isn't about being an artist. It's simply about being able to represent what is actually happening in a particular circuit. So I'm going to go through and show you some of the symbols for the circuits. These are common symbols. They're all listed in your books. In your book, I should say. So if you forget them, you'll have this list, and then you can always go back to the book. And if you just look up in the index, circuit symbols, it'll take you right to the page where you're going to find these. So the first thing, obviously, in an electrical circuit, we need something called a wire. Okay, the symbol for wires is pretty straightforward. It's just simply a straight line. So it's the connecting thing to the different devices. After the wire, we need something to provide the energy, to provide the source of power for the electric circuit to get everybody moving, and that is typically going to be a battery. Now, there's two ways to think about a battery. So first of all, we can draw a single cell, and a single cell would look something like this. It's going to be one long line and one short line. Okay, the long line is always the positive end. The short line is always the negative end. That's always true, whether you're looking at a cell or whether you're looking at a battery. This is what is providing the electric voltage. So this might be 2 volts or 20 volts, 120 volts. This is the thing that is providing the voltage or the power supply or the energy supply for the circuit. Now, there's a related thing called a battery. Okay, and the only difference with a battery is that a battery is a collection of cells. A cell is a single thing, and then when you collect together several cells, then you get something called a battery. So when you pick up a battery, like let's say your AA batteries, it is actually a collection of smaller cells. If you could look inside, you would see that there were alternating layers of these different materials that were providing the push for this electrical circuit. It doesn't really make a difference to me. I generally speaking, I'm just going to draw one cell because I don't know how many cells are in the actual battery. You know, it could be 10 or 20 or 100. I have no idea. I'm not going to break the battery open to find out. But I do know that all batteries, I mean, literally the word battery means a collection of cells. So it's a battery requires you to have multiple objects, whereas a cell only requires you to have a single object. So either of these two symbols for batteries would be fine with me. Just remember that the longer line represents the positive end of the battery, and that is where the conventional current leaves. Conventional current leaves the positive terminal, travels around the circuit, and then returns back through the negative to be re-energized by the battery. All these little coulomb of charges, they come back to the battery. They've been depleted of their energy. Now they pick up a new supply of energy from the battery, and they carry that energy out to the circuit. So besides the battery, which provides the power supply, we want we want to supply power to something. So let's take a look at, first of all, a light bulb. So a light bulb is going to be symbolized by a circle with a kind of a curly line or kind of a curlicue. This is because the early light bulbs did actually have these little filaments, which were kind of like this little coiled wire. The newer light bulbs didn't work in quite the same way, but the incandescent or the fluorescent bulbs, the compact fluorescent do have kind of a curly portion to them. So in any case, again, this is like a historical artifact. This is the symbol that was used to represent the light bulbs, and we're going to continue to use it. Now, this is like a specific device, and this is for turning into light, obviously. But in general, any object that uses electrical energy can just be represented as a resistor. This is really important. In order to get the energy out of the electrical system, you have to put some resistance in the way. If you don't put some resistance in the way, then the energy stays in the system. It just continues to travel around and around and around with no change. So generically, we can use this idea of a resistor as a way of extracting energy. And the symbol for it in the United States is like this, kind of a squiggly line. And I guess it's there to just represent that something needs to happen. Something needs to slow the current down or stop the current or to extract the current. So this kind of agitated line represents this object pulling energy out of the electrical system and leaving less energy in the charges as they pass by. Now, besides the resistor, we will also use something called a variable resistor. And this is going to be really helpful for our labs because it's going to allow us to change the resistance. So if we want to turn the current up or turn the current down, we can adjust the resistance, and we will be able to do that. Now, the variable resistor looks very similar. So like all circuit elements, it has a way to get in and a way to get out, a way to get in, a way to get out, a way to get in, a way to get out. It always has 2 connection points, but this one's a little bit different because it actually has 3 connecting points. And here's the third one. So there are the 2 connecting points on the ends, and then there's the connecting point in the middle. And let me show you what a variable resistor looks like. So I have 2 examples of variable resistors. If you have a switch in your house that allows you to dim the lights, where you can turn the lights up or down in a smooth, continuous motion, this is the device that you have. You have a device here which is changing the resistance of your circuit. And as it, for example, if it increases the resistance in the circuit, then that's going to make it harder for current to flow to that particular part of the circuit, and therefore your light bulb is going to get dimmer. If on the other hand you want your light bulb to get brighter, then you want to lower the resistance in that part of the circuit, and that will allow more current with its energy to travel to that portion of the circuit and then expend that energy. So just like I pointed out in the diagram, you can see that there are 3 connecting points, 2 on the outside and 1 in the middle. The one in the middle is actually connected to this guy. So you'll notice that as I turn the dial, I can change this. So let me bring it over to here, and let's say that, for example, I had connected this to the circuit. So now the current would flow in through here. It would go up to, let me turn this out of the way for a little bit, up to this portion right here, which is connected. And I know it's a little difficult to see maybe in the video, but this is just a long wire that's been wrapped around this insulating material. It's made of ceramic. It's wrapped very tightly around it. None of the wires touch each other. There's a little bit of space between them. And in order to make sure that the wires don't come together and touch each other, they've essentially glued them together so that the wires can no longer move. So essentially what's inside this big C portion right here is just a big long coil of wires. I mean, this wire, if I were to take it out and to stretch it out, I would imagine it would probably be about 5 or 6 feet long. So it would be quite long. So what ends up happening is right now, if I turn this over to here, the current will come in here. It will travel up, but it's going to just go to this middle guy right here, which is going to bring it to the center and then out through the middle. So this will have very little resistance. So if you want your light to be very bright, you would connect it like this. Now, if I want to make the light bulb to be a lot brighter, or much dimmer, I should say, is I would turn it like this. Now I've added about 15 to 20 loops of wire, and those 15 to 20 loops of wire have more resistance. And so now I've put more resistance into the system as a whole, and as a result, less current is going to flow. And the more wire that I add in, so now I have all of this wire added in, the more resistance that I get, the less current goes there, and therefore the less light that gets there. If I turn it all the way around to this end, I might actually be able to turn the light all the way down so that there's no light coming anymore because I've included so much resistance. So this is a pretty large variable resistor. I have a smaller one, but again, really important thing to point out, the 3 connectors, the one on the right, the one on the left, and then the one in the middle. So the one in the middle is always going to be connected. That's the guy, that's essentially our escape route. And then the question is, whichever end you decide is here is going to determine which end is the maximum and which end is the minimum. So I might connect it over here so that this is my maximum setting, or I can switch it. I can reverse the wires, and then my maximum setting will be on this side. So that as I turn this little device, I'll be increasing the amount of wire that is in that system, and as a result, I'll be changing the resistance. Okay, so variable resistors are really helpful because it's going to allow us to do controlled experiments where we can see exactly what's going on inside of the electrical system. All right, so that takes care of the basic things, but there are a couple other really important things to think about. So let's take a look at this guy called a switch. You may see that in some circuits. There'll be a solid dot right here, and switches are always drawn in the open position. Now, regardless of whether the switch is actually open or closed, it is always drawn in the circuit diagram in the open position, similar to like architectural drawings. The doors are drawn in the open position because otherwise it's kind of hard to tell that it's a door. It just looks like a wall if you just draw a straight line. So in order to indicate that it's a switch, we put the solid dots and we leave this guy in the open position. Now, if you are being instructed that the switch has been closed, you'll just mentally imagine what would happen if the switch was closed. This is how the switches work in your house. They essentially have a point that is disconnected with the wires. Right now, this would be if the switch was in the on position, and the current would be flowing through my hands right here. But if I want to turn off the object, I'll break that connection. Now the switch is open. Now current can no longer flow because it's not a closed circuit anymore. It's not a loop. So because it's not a loop, the current will stop flowing. When I want to turn the light back on, I bring the guys back down in contact, the current begins to flow. That is exactly how the light switches in your house work, and really, for that matter, almost every switch works on a similar principle. Now, one thing that we will not see as much, but you will occasionally see it in diagrams, is something called a ground wire. It looks a little bit like the battery, except that we're going to continue to draw smaller and smaller lines, and then they end. This is really important. This is meant to represent the Earth. I don't know if it's supposed to be like the layers of the Earth, or I don't know why they use this symbol for it, but what it essentially means is that this wire goes down and is connected to the ground, and I mean literally connected to the ground. Most likely the wire is buried in the ground, or it goes down quite deeply before eventually it comes in contact with some of the rocks. The ground wire is a way of dissipating or removing electrical energy if for some reason there was too much. So it is something that is connected in your house. That's the third, when you plug in the outlet, you have the two flat portions, and then there's usually a little round one. Sometimes there is, sometimes there's not. Things that have very large amounts of current or have very sensitive electrical equipment, they will have a ground wire so that if too much current flows through there, it gives a place for the current to go where it can be allowed to be released, essentially. Released in a safe way. Okay, so that brings us to two more devices. These are going to be the devices used for making measurements. Sorry, I misspelled that. So ammeter. The ammeter measures the current because current is measured in amps. So it's symbolized with a little circle with the letter A in it. In the beginning, we won't draw this too often, but as we get to more and more sophisticated circuits, we'll definitely expect that you can draw ammeters in place. If I asked you to add an ammeter to a circuit, you'd know how to do that. And then secondly, besides measuring the current, we'd also like to be able to measure the voltage. And so we'll do that with something called a voltmeter. And you'll see this is what the circuit symbol looks like, and then you'll have plenty of opportunities. We'll be bringing the voltmeters out very soon so you can get a look at them and learn how to use them. But ultimately, the voltmeter measures the voltage. So measuring the current and measuring the voltage is the ammeter and the voltmeter. One last little thing to think about is whether there is a connection. Normally, we'll draw our circuit diagrams in such a way that we'll try to make sure the wires don't cross each other, because then that's kind of confusing. But sometimes we just can't do it. Sometimes you just can't make the drawing without having the wires cross. And so in order to indicate that those wires are actually connected to each other, that they're not just like this, where they pass over each other, right, but they are actually down touching each other and in contact with each other, then we put a little solid dot right there. If we want to indicate that there is no connection, then we will draw the exact same diagram, but we won't put that heavy dot. And that heavy dot being absent just indicates to you that the wires are not actually touching each other. So they may actually be physically touching each other, but wires are usually coated with plastic to prevent the current from being able to escape. And so in situations where the wires are passing but not touching, we'll draw this symbol. And if the wires are actually touching each other so that current can flow from one wire to the other, then we'll draw it like this. And you'll see all of these devices. We'll bring out light bulbs, resistors, we'll have variable resistors you've already seen. We'll use cells. We can bring out some switches. We'll definitely be connecting ammeters and voltmeters. Most of the time we won't have to deal with this situation because we can usually draw the thing without having to worry about lines crossing each other. But as the diagrams get more and more complicated, we may have to draw them like this. It may not be possible to draw all the wires and not show any of the wires crossing each other. And so we'll use this convention of the solid dot for connecting and no solid dot for not connecting. And so, here at the beginning, you're just being asked to be familiar with the symbols. You really just want to memorize these symbols. And once you've got them memorized, it's going to make it so much easier for you to draw the circuit diagrams, and then you'll be able to read the diagrams. This is really important. I'm most concerned with you being able to look at a diagram of how some electrical equipment is connected and just recognize all the players and then be able to solve that problem. And the first step is to recognize the symbols.